In this lesson, we're going to look at stoichiometry some more, but this time we're going to look at it with respect to solutions and using molarity and volumes. We've seen this diagram before, and we've talked about going from mass to moles, and then moles of our unknown to the mass of the unknown. Now we're going to add in something else. We're going to look at the volume, or looking at going from liters to moles using the molarity of a substance. So we have two more connections we can make. And we've actually already looked at how we get from atoms and molecules to moles, as well as from volume to mass using density. Ultimately, our goal is to get to moles of our known substance, use our coefficients from the balanced chemical equation to find moles of our unknown, and then to find whatever's actually being asked for in the problem. Just because we start with a mass doesn't mean we have to end with a mass. We can start with liters and go to moles, and then grams. We could start with molecules to moles to liters. Any pathway possible. The only thing we have to remember is that we have to go through moles and use the coefficients from the balanced chemical equation. The pathway of the problem will depend on what information you're given and what information you're trying to find. Let's look at an example. How many milliliters of 0.10 molar lead nitrate are required to react with 75 milliliters of 0.20 molar NaI? First thing we need to do is to make sure our equation is balanced, which it is in this case. Next, I'm going to get the information out of the problem and summarize it, so that way I'm not having to reread the problem multiple times to remember what numbers are there. And it also helps me sort data so that I don't get anything mixed up. I go back to the problem. It says how many milliliters of my lead nitrate. So I'm going to put milliliters equals question mark. That just reminds me what I'm looking for. And it says we have 0.10 molar lead nitrate. So I'm going to put my 0.10. And remember, when we have molarity, I don't write the big M. I write moles of my lead nitrate over liters. So I'm writing it in that expanded form so that when I go to set up my problem, my stoichiometry problem, I can see what's in the numerator and what's in the denominator. Next, are required to react with 75 milliliters. And this is talking about the NaI, so I'll put that below the NaI. And we have 0.20 molar NaI. So I have 0.20 moles of NaI per liter. Now I've summarized my information, and I've also sorted it between each substance. So it's going to be a little bit easier to keep track of. Just like with any other stoichiometry problem, I've got to figure out how I can get to moles. And when we looked at dimensional analysis, we looked at starting with a simple unit. Remember, molarity is not a simple unit. It's a relationship between moles and liters. And so what I'm looking at is which substance has enough information to find moles. And that would be for the NaI. I know milliliters, it's a simple unit. That's great. And I also know that I can get from volume to moles of NaI using the molarity. I'm going to start with my 75 milliliters. Then I'm going to use my metric prefixes, put the 1 with the prefix, put the meaning with the base to convert to liters. Milliliters will cancel out. I'm going to have liters on the bottom and moles on top using my molarity of the NaI. Now liters will cancel out. Now I need to use the coefficients from our balanced chemical equation. So 2 moles of NaI to 1 mole of PbNO3, moles of NaI will cancel. Next, I'm going to use the molarity of the PbNO3 of 0.10 moles per liter. My moles of lead nitrate cancel. And again, I'm going to use my metric prefixes to convert from liters to milliliters. Put the 1 with the prefix, put the meaning with the base, and liters will cancel out. And I see that I have units of milliliters left, which is what I want for my answer. I can also look and see that 10 to the minus 3 is going to cancel out. At the beginning of the problem, I have it in the numerator. At the end of the problem, I have it in the denominator. If you want to cancel it out, great. If you don't and you plug both those values in, it's not going to actually change your answer. When I do the calculation, I get 75 milliliters of lead nitrate. And just because it's the same number in this problem doesn't mean it's going to be the same number in every problem. So you have to work out the stoichiometry. A common place that we're going to use solution stoichiometry is dealing with titrations. And a titration is just an analytical lab technique to help us identify something about an unknown solution. Okay. And when we get to that equivalence point, what that means is the concentration of H plus equals the concentration of OH minus. And that takes into account the formula if we have H2SO4 where there are two hydrogens, or magnesium hydroxide where there are two OH groups. So we're worried about the concentration of the H plus and the OH minus, not necessarily the concentration of the acid and the base. And this is something when you take a lab class, you'll learn how to do a titration, and we can graph this. So pH is a measure of acidity. We can talk about adding volume of base to our acid, which we don't know the concentration of. And we use indicators, which we've talked about before. And when we see that color change, we know we've reached that equivalence point. And this is one of the big places where we use this solution stoichiometry as in titration. And some students get caught up in the whole it's a titration, but really it's just a fancy stoichiometry problem. The only difference between titration problems and other stoichiometry problems is we're dealing with a volume and a molarity to get to moles, but it's still the same process. Go to moles of our known, use our coefficients from our balanced chemical equation to get to moles of our unknown, and then finish the problem. Same thing over again. We call it something special, but it's really just a stoichiometry problem. Let's look at another example. What is the concentration of a 25.00 milliliter NaOH solution that requires 16.75 milliliters of 0.250 molar H2SO4 to titrate? Sorry, I left out that concentration. Again, saying how much it requires, we're just saying what is the stoichiometric amount of substances? What is the stoichiometric relationship between those substances in this reaction? So just because we call it a titration doesn't change anything about the problem. I'm going to collect my information just like we did before. It says, what is the concentration? We're only dealing with molarity, so we say molarity equals question mark. We have 25 milliliters of our NaOH. We have 16.75 milliliters of the H2SO4, and our molarity is 0.250 moles per liter of the H2SO4. Just like with any other stoichiometry problem, we do need to check that it is balanced, and we're actually missing a 2 in there, so we'll put that in there. We need to find molarity. Let's look at the definition of molarity. Molarity equals moles over liters. Now, when I look at my NaOH, I see that I have the milliliters of NaOH. Can I find the liters of NaOH? We can find that. So we know the volume, we know the liters, or we can find the liters of NaOH. So we need to find the moles of NaOH. And that's where our stoichiometry problem is going to come in. Just like in the previous example, we're going to start with our 16.75 milliliters. The volume we know, it's a simple unit. H2SO4 is the only substance I can get to moles with. Use my metric prefixes. 1 milliliter is 10 to the minus 3 liters. Milliliters will cancel. Then use my molarity of H2SO4, and liters cancel. Next, I use my mole to mole ratio for my balanced chemical equation. 2 moles of NaOH to 1 mole of H2SO4, and moles cancel. Now, I look at the units I have left here, and I have moles of NaOH, which is exactly what I'm looking for to find the molarity, because I know the volume, I just need the moles. So now I can solve the problem at this point, and I get 0.008375 moles of NaOH. But remember, that's not my answer. That's the moles, and I want to find molarity. Now, I have my moles, I have my liters, or I can find the liters, so I can calculate the molarity. And I end up with 0.008375 moles of NaOH over 0.02500 liters of my NaOH solution. And I find I have 0.335 molar NaOH solution. Let's look at another example where we're not given the equation. What volume of 0.175 molar HCl is needed to titrate 30 milliliters of 0.200 molar barium hydroxide? And you're given a hint here to write a balanced equation. We're going to start with our HCl plus our BaOH2. Those are our two reactants. HCl is an acid because it starts with an H and it's one of those 6 strong acids. Barium hydroxide is a strong base. It's a metal hydroxide. So we have an acid and a base reacting, and that's going to produce salt and water. And the salt that it produces will be BaCl2. I have my Ba, which has a 2 plus charge, Cl, which has a -1 charge. So we have to redetermine that formula when we write out the equation, BaCl2 plus water. Every acid-base reaction produces salt and water. Now we need to balance the equation. So we need a 2 in front of HCl and a 2 in front of H2O. Because remember, we're going to need that mole to mole ratio from our balanced equation to set up our stoichiometry problem. We're looking for the volume of HCl. That's what's being asked for. And it tells us our molarity is 0.175 moles over liters. Again, rewriting that molarity as moles over liters just to remind me. I have 30 milliliters of BaOH2, which has a concentration of 0.200 moles per liter. Now I can go about setting up my stoichiometry problem. I look for my simple unit and for what substance I can get to moles. And BaOH2 is the only one that applies there. I have 30 milliliters of BaOH2. Again, use my metric prefixes to convert to liters. So milliliters cancel. Then I use my molarity of BaOH2 to get to moles, with liters canceling there. Now I can use the coefficients for my balanced chemical equation to set up my mole to mole ratio for 1 mole of BaOH2 to 2 moles of HCl, and moles of BaOH2 cancel. In the previous problem, we stopped at moles because we were trying to find moles. We had the volume. In this case, we're trying to find the volume, so we need to take it one step further. We know the molarity of the HCl. We put 0.175 moles on the bottom and liters on top, and moles cancel out. And the volume units are not specified here, but because we started with milliliters, we're going to end with milliliters. So we convert from liters to milliliters, and liters cancel out. And again, I can cancel out the 10 to the -3 because I have it in the numerator and in the denominator. Now we set up our calculation in the calculator and we get 68.6 milliliters